All right, this is chapter 5, homework for Physics 151, beginning with the questions. Question number 2. It says, based on the submicroscopic structure of solids, liquids, and gases, explain why gases are easy to compress, but liquids and solids are very difficult to compress. So if I consider a gas, the particles are spread apart a lot. And so if I have this, say, in a container, and I want to compress it, it's very easy to compress it because I push down with a certain force. It's very easy to compress it because those particles are really far apart. So you just sort of push them a little closer together, which is very easy to do. However, with a liquid and with a solid, for the same reason, in a liquid, those particles are already really close together. And so when you try to push them closer together, you can't push them any closer together, so they're incompressible, we would say. And that's same for most fluids and for practically all solids, that they're incompressible. And it's just because of the spacing of the molecules or the atoms that make up the fluid, the liquid, or excuse me, the liquid or the solid. Question number 5. What is the difference between density and mass? Well, density is related to mass. Density is equal to the mass divided by the volume. So you can have a small mass of something that has a very high density. Like, for example, you could have a very small mass of lead, but lead has a high density, a very big density. And if you have a small mass of lead, that also means that you have a small volume of lead. On the other hand, you can have a very big mass of something that's light, like, say, I don't know, feathers, which are very not dense at all, but feathers have a small density. Right? But if you have a big mass, that means that you're going to have a very large volume of feathers. Give an example of how density of an object can be used to identify the substance of which it is composed. Well, this is a pretty good method to determine what are unknown substances. If you know the volume of an object and the mass of an object, then you can calculate its density. And if you look at our table, this is on your equation sheet, but it's also in the book. You'll find a table of densities. Let's see here. And measuring the mass and the volume, you can determine what is the density. They do this for gold to determine what is made of gold and what's not made of gold by measuring the density of the object. All right, here we go. I've updated your equation sheet to include chapter 5 equations. All right, we'll need that later. I'll just leave it for now. But anyway, you'll find in that table, I'll show you in just a bit, the density for a given substance. And say gold, for example, aluminum, brass. And you'll find that they all have different densities. And you can differentiate between unknown materials by their density. All right, question 5. Question 9. What would be more effective in keeping a bed warm in an unheated house, a hot water bottle or an equal mass of brick with the same temperature? Well, you want to ask yourself, which of these has the higher specific heat? And that material will be better to keep the bed warm. And you can know which has the higher specific heat. You can ask yourself, which one of these is going to stay warm the longest? Right, that's going to be the same question because the one that stays warm the longest is the one that has the higher specific heat. And of course, if you've ever had a brick and a bottle of hot water, you know that the answer to this is that the hot water stays warmer the longest. All right. What this means is that when it has the higher specific heat, remember our equation is Sm delta T. If this value is big, that means to get a certain change in temperature, you're going to have a lot of energy. All right, so the bottle of hot water requires more energy to heat up than does the brick, and so that energy is dissipated throughout the night into your bed to keep it warm. Let's see if our table has come up yet. Okay, here we go. So if we look at our equation sheet, here's our densities that I told you about. So you see the density of gold is quite a bit more than the density of aluminum. In fact, gold differs quite a bit from others as well. And then here's our specific heats. Let's say here is the specific heat of water, which is fairly large, about 1, and then we'll compare it with aluminum. I think that's about the same as a brick. It's about 5 times that of aluminum or other. It's quite a bit larger than most solids. Water has a very high specific heat. All right, the next question is question 10. Temperatures in coastal areas are generally more moderate than temperatures inland. For example, temperatures in San Francisco are neither as hot in the summer nor as cold in the winter as in Sacramento, 90 miles inland. Explain why this is so. This is because of the specific heat of water is very high. All right, so you have this huge body of water, the ocean, and it does not change temperatures very quickly. And so in the wintertime, that body of water is relatively warm because it's been heating up all summer, all right? And then into the winter, it retains some of that heat into the winter, and so it makes for a moderate temperature. And then in the summertime, it's been cooling off all wintertime, and in the summertime, then the body of water is cool. So in the summer, you have your water and your inland, and the water is relatively cool because it takes a long time to get rid of all of that heat that it's to get rid of all of to gain heat in order to make it warmer. And then in the wintertime, here's our water, our land, and in the wintertime, this water is relatively warm because of the high specific heat of water. All right, question 12. It says in cooking, more heat is required to keep an uncovered pot of water boiling than one that is covered. So if I have this pot of water and it's sitting on the stove, and then I have water here that's boiling, it's at 100 degrees Celsius and boiling. If this water is uncovered, we have convection, several modes of heat transfer that occurs. Primarily convection. Convection because I have these air currents that come down into the water and capture some of that heat and bring it away. But you also have other modes as well. Conduction. Well, conduction sort of occurs between the hot water and the air. And then you also have radiation in a sense, but mainly convection and conduction. Now, if you put a cap on this, then it gets rid of that conduction and the convection. And so that heat transfer is basically eliminated, largely eliminated. So you're not losing heat to the air around the pot. That's question 12. We're going to skip question 14. I'll go straight to question 16. I'll update your list. A cold room with high humidity feels less chilly than a dry room with the same temperature. Remember, what is it that cools our body? It's the evaporating of sweat. So well, that's kind of a lopsided guy. But I have these little droplets of water on my body, and they evaporate into the air. And when they evaporate, they take a lot of energy. That's because the latent heat of vaporization of water, M, we can calculate the energy that it takes away by this, where LV is the latent heat of vaporization. Or that's the amount of energy per unit mass that is required to change a material from a liquid to a gas. And that's what happens when you sweat, is that the water that's on your skin evaporates and turns into a gas. Now, in a low humidity room with a very low humidity, this evaporation occurs more readily. In a high humidity room, the evaporation doesn't occur because the air around you is already saturated with water. And so the evaporation of the sweat off of your body does not occur readily. Right? So you feel warmer in a high humidity room because the sweat doesn't evaporate from your body as readily. All right, now question 21. Closing curtain windows on a cold night reduces heat loss. What methods of heat transfer are slowed by the curtains? We just got some new curtains. We found quite a difference, actually. So let's say this is your room. Here's your window. House. Here's our window right here. We have several methods of heat conduction, basically all of the methods of heat conduction that occur. We have radiation. Radiation is probably the least significant, the least important. You have radiation that leaves through the window, and putting curtains on your window will close that. We have convection and conduction, which sort of happen at the same time. So in convection, you have these hot air currents that will move air around the room, and conduction, where heat will leave the room when those hot air currents come into contact with the window. Heat will leave the room by conduction through the window. Right? When I put a curtain on that window, it eliminates the radiation. It basically eliminates the conduction, which paired with the convection limits the amount of heat that you lose in your room. All right, let's go on to the problems. Problem number 1. How many calories of heat would be required to raise the temperature of a 45 kilogram person by 2 degrees Celsius? All right, so I have a mass of a person is 45 kilograms, and I want to change the temperature of that person by 2 degrees Celsius. I need to know what is the specific heat of a person, of their body. If you look on your table, there's an average specific heat for the human body. It's 0.83. The human body consists of mostly of water. Specific heat of water is 1. So you'd expect it to be close to that. So 0.83. This is in, check the units on that, calories per gram degree Celsius. Calories per gram degree Celsius. And then I can find my Q. It's SM delta T. That's 0.83. Calories per gram degree Celsius. Then I need to convert my 45 kilograms into grams. That's 45,000 grams. I know that because my specific heat is given in terms of grams, and then my change in temperature, which is 2 degrees Celsius. And that gives me the number of calories, 0.83. $7.75,000 calories. All right, but remember, food calories are kilocalories, so that is 75 kilocalories. Or we sometimes write it as 75 capital C calories, and those are food calories. Now, question number 3. I want to know what Fahrenheit temperature corresponds to absolute zero. So what in degrees Fahrenheit corresponds to 0 Kelvin? Let's go to our equation sheet. We can find our conversions between the different Fahrenheit and Celsius scales. Fahrenheit is 9/5 T plus 32. So T degrees Fahrenheit is equal to 9/5 times T degrees Celsius to plus 32. But I need to know what is 0 Kelvin. And you'll have this actually. I'll update your equation sheet. Let's see. T in degrees Celsius is equal to T in Kelvin minus 273. So 0 degrees Celsius, or excuse me, T degrees Celsius is equal to 0 Kelvin minus 273. So T in degrees Celsius is equal to negative 273. I'll include this on your equation sheet. Sorry, that was an oversight. Now I want to convert that into degrees Celsius. So it's 9/5 times negative 273 degrees Celsius plus 32. I get minus 459 degrees Fahrenheit. And again, I will include that conversion. T degrees Celsius equals T Kelvin minus 273. I'll include that on your equation sheet. All right, number 3. Now number 9 says the Golden Gate Bridge has an overall length of approximately 2,800 meters. If the bridge experiences extreme temperatures from minus 20 to plus 40, so delta T is going to be 40 minus negative 20, so that's 60 degrees. It experiences changes in temperature, 60 degrees Celsius. What will its change in length be? What is delta L? We also need to know the coefficient of linear expansion, and it says that that bridge is made primarily of steel. The coefficient of linear expansion for steel is 12 times 10 to the minus 6. 12 times 10 to the minus 6. And then I can find delta L as L alpha delta T. That's on your equation sheet. This is 1 over degrees Celsius. So I'm just plugging in numbers now. 2,800 meters times 12 times 10 to the minus 6. 1 over degrees Celsius times 60 degrees Celsius. I get 2 meters. 2 meters. This bridge changes going from minus 20 to 40 degrees Celsius. 2 meters in length. All right, number 9. After that, number 13. How many calories of... Oh, no, I'm sorry, not 13. I'm sorry, I've already done this one. So let's go up. This was number 13. Sorry about that. But I skipped number 1. So let's do number 1. Normal body temperature is 37 degrees Celsius. Convert this to Fahrenheit. So I want to know what this is in degrees Fahrenheit. I'll go back to my equation sheet. In order to convert degrees Celsius to Fahrenheit, 9/5 T degrees Celsius plus 32. And this is equal to my temperature in degrees Fahrenheit. So that's 9/5 of 37 plus 32. You get 98.6. To be expected. And what is the temperature in degrees Celsius of a person with a fever of 104 degrees Fahrenheit? So 104 degrees Fahrenheit equals how many degrees Celsius? Go back to my equation sheet. 5/9 T Fahrenheit minus 32. (104 minus 32 is 72 times 5 divided by 9. You get 40 degrees Celsius. All right, again, that's number 1. So now we're back with 23, number 23. If a 30-gram lead bullet with a speed of 600 meters per second strikes a practice target and half of the thermal energy is absorbed by the bullet, what is the temperature increase of the bullet? All right, so this bullet has a certain amount of kinetic energy. It's equal to 1/2 mv squared. I need to determine the total energy of the bullet, and then half of that energy is going to be converted into thermal energy. So it's 1/2 of 30 grams, which is 0.03 kilograms, times 600 squared. (5,400 joules). All right. Now half of that is going to go into thermal energy. So Q is going to be 5,400 joules over 2. It's 2,700 joules. Now, when I'm working with Q, though, I need to be in calories. Let's see, I think I still have this on the equation sheet. No, but I'll provide it for you. See, make sure that I get this right. 1 joule okay, so 1 calorie is 4.2 joules. So I want to convert these to these 2,700 joules to calories. So 2,700 divided by 4.2. 640 calories. So this bullet absorbs 640 calories, and now I want to determine what is its change in temperature. So I go back to our calorimetry equation, Sm delta T, and I'm going to solve this for delta T. I divide both sides by S and M, and I get delta T is equal to Q divided by S times M. Q is 640 calories. I look up the specific heat of lead that's on your equation sheet. See, the specific heat of lead is 0.030 calories per gram degree Celsius. And then the mass of my bullet, notice that this specific heat is in grams, so I have to use my mass in grams, and that's going to be my change in temperature in degrees Celsius. So it's 640. Oh goodness, 700 degrees. It heats up 700 degrees. That's assuming that most of the energy goes into or half of the energy goes into the bullet. But even if you're not half, you're still looking at a very significant temperature rise in this bullet. All right, let's see. That was 23. I think there's just one more. 49. Calculate how much perspiration a person must evaporate during physical exercise to get rid of 100,000 calories of heat. So Q is equal to 100,000 calories, and I want to know how much sweat a person must evaporate in order to get rid of that. This goes back to our latent heat of vaporization. That amount of energy is equal to M times the latent heat of vaporization. So I want to know what is the mass. So it's going to be Q over the latent heat of vaporization. That's 100,000 calories. Let's go back to my table and get the latent heat of vaporization for water. Here's water. I need the latent heat of vaporization, 540. And this is in calories per gram. So 100,000 over 540. 185 grams. All right, 185 grams of water.